Okay. All right, so we were attacking this problem here, the cylinder rolling on a incline. There is roll without slip, and we had found this differential equation of motion using the center of mass as the point with respect to which you compute the angular momentum and you apply the second law of Euler, which in the general form with respect to a generic point Q is written down here. So I just wrote down a few things that we had found last time. I was almost going to circle the equation because that's what we found. But again, the final answer is not really, yeah, it is the goal, but it is the procedure that leads you there that is more important. So we'll find the same thing, doing it with respect to other points, just to see how to play with these different formulations. And I think this was the H bar we had. And again, I computed once. I'm not going to go back to compute any more angular momentums using the tensor of inertia. I do it once with respect to the center of mass because that's the beauty of being in a coordinate system fixed to the body. And then at the most, I will move to another point using this expression down here. So there's just a few things they really need to remember. These two here for the Euler's law, and that's pretty much it. So before we start, yes?
There's RQ minus R bar, and then the derivative is R bar minus RQ.
Because that's what you find. I think we spent a lecture to show why this happens. There may be a sign error, but I don't think so. I think that's what you get. You can also switch these two if it's easier to remember. Plus RQ minus R bar. Yeah. Make sense?
Oh yeah, that's what you had last time.
Yeah. I mean, I probably have just swapped the RQ with R bar and add a plus here. Yeah. So something like that. So, but again, I'm terrible at memorizing stuff. If you see an error because I wrote stuff by memory, let me know. You know where these things are in your book. That's the point. And I know this, and I do the same. If I don't remember them, I check them on the book or my notes. I just focus on how to use them. That's the point. So, but before we start here, I wanted to highlight a couple of things. One, we are already almost 10 days from the day when I think I sent you the test. So if you have things you need to discuss, now it's the time because I'm not going to drag discussions forever. I mean, the grading is done. I think you've had enough time to look at the problems. If you have issues, come today, maybe Wednesday, then we're done. So the other point is I sent you a list of a few problems that you can skip from chapter 5, collisions. I'm not going to do collisions probably. So you can initially skip those. And again, I'll decide on which topics to focus the most along the way sometimes. So I may find that some other problems you don't really want to solve them. We'll see. But I think the rest of them should be fine. I won't repeat this enough. We are at a point where you guys need to remember every single thing we've done. You need to remember kinematics. You need to remember the transport theorem, of course. The properties of a rigid body. You need to remember everything that we've done, because in all these problems, this is a very simple one. Next time, probably I'll do a 3D case. I'll probably bring one of my toys, a gyroscope. So we'll look at that, how it moves, and then we'll try to find some equations. But this is just one rotation, and it still takes some time, and it still requires you to remember, or at least know where things are in your book. So you can't ask me what is going to be on the last test. Is it only going to be the second half of the class? Yes, in principle, because this is the second half of the class. But if you don't remember kinematics, so it's actually the entire course. Unfortunately, that's how things are set up with dynamics. You can't just ignore the first part and then move on with the second. That's not how it works. So that's a kind of a pointless question. And again, it is how you develop the solution. It is how you apply the principles that matters. So I'm going to be even stricter if you want in selecting if you've done things right or not. If you confuse coordinate systems with reference frames and all these basic things, that's something that will be penalized. So just making sure that we are on the same frequency here. Again, you need to really refresh everything. So we've seen last time that with respect to the center of mass, the moments of forces that are acting on point Q really don't go away. So this is the C point. This is, you would have here reaction, the normal reaction from the ground. and then some static friction that allows the disk to roll. And we have noticed how, well, of course, if you do compute m bar, these two still remain there. They don't have a zero. Well, this doesn't, but this does. And so we had to use both first and second Euler's laws together to solve the problem. But if you actually think before you do anything, and you realize that picking point Q may make your life easier, you may not need to do so. So let's try to see what happens when we pick Q. If we pick Q, it means, starting from the second law for rigid body, it means that I'm looking at this. I need to transport my angular momentum to the point Q first. Then I need to take its time derivative, of course, here. And then I will have to add to the moment of the forces with respect to point Q this term here. So what I need to find are which things here in these two. So I have h bar. I computed it once and for all. That's what I think I've told you like 10 times at this point. You go straight to h bar, you compute it, and then if you need to move, you use these results. So this is the first thing. What do I need to know? I need to move to point Q, right? I need HQ in G. Remember, G is inertial. So h bar is it's that m r squared over 2 theta dot Ez, and that's that, plus, what is RQ minus R bar? R bar is RC. C is the center of mass. I think also this we computed like 10 times last time, probably. Is it? R big EY, bless you, cross with, what do I put here? You really should know what this is. If you don't, it means, right, why? Because there is roll, so the velocity of the point Q as part of the disk. And we said that that's the one that we're actually going to use here. We said last time, let's focus on the point disk part of the point Q part of the disk. So let me add that if you want. With respect to a generic reference frame, is the same as the velocity of point Q is part of the ground with respect to the same reference frame. And so this is obviously 0, and so that VQG is 0. So what is minus V bar G? I think we've done this last time. I don't remember it. Can you tell me? What that is? I'm just rewriting stuff to gain some time. What is the velocity of the center of mass? Right? Where did this come from? The minus in front. Remember, where did this come from? I've used the roll without slip condition. So the velocity of Q is 0, then the velocity of a point on another point of the rigid body is, the difference between the two is omega cross the vector between the two, right? One of the properties for rigid bodies. So, okay, let me compute this thing here. What I have is that m r squared over 2 theta dot. Let me use big EZ because they are the same thing. What is EY crossed with EX? Is EZ, right? Is it? Is there something missing here? Of course there is. It wasn't making sense dimensionally. The mass was here. The mass is here. The mass is here. Sorry, so you were saying is minus, is it minus? It's positive, right? It's EX crossed with EY crossed with EX. Okay, cool. So it's m r squared. Now it makes sense. Same dimensions. M r squared theta dot EZ. Okay, and so this is 3 over 2 m r squared theta dot big EZ. This is my HQG. So, can I erase this? at least the top part, so I can copy this here. Okay. So now I'm looking at this one here. I still need, so I have HQG. I can take its rate of change, of course. Its rate of change in G. It's quite simple, right? 3 over 2 m r squared theta double dot big EZ, because the big E's represent the coordinate system which is fixed to the ground. That's that. What is MQ? I really want to go slow, even though this is a simple problem. I don't care. So it's the moment of forces. Remember, this is your point Q down here somewhere. And whatever it's acting on this point doesn't matter, because I'm computing the moment with respect to the point. So the only thing that is left is the force of gravity, mg, right? So it's this vector here that goes from Q to C. So it's going to be minus REY. Correct? Cross with mg. Now you tell me what mg is in that big E frame. What's in here? Look at your notes. Don't make me look at mine. Or look at that. There was some cosine, sine, something. So this is G down here. Is cosine, huh? That's it? Okay, let's do it. EY cross EY 0. EY cross EX minus EZ. There's a minus there. It's a plus. So I see it R M G sine of beta EZ. Agree? Did I miss anything? No? Okay, so this is my MQ. Put it up here. Easy. What else am I missing here to execute this relationship here? I have the left-hand side. I almost have the right-hand side. R bar minus RQ it's easy. What am I missing here? Acceleration of Q. Remember, Q is a point which is part of the disk and happens to be the point of contact, at the point of contact. Now, you guys need to tell me how I compute that. Because if you don't know how to do it, you are in big trouble at this point. Acceleration of Q in G. Let me add, this is part of the disk. How do I do this? Someone has to tell me. It may be that it's theta double dot R something, but I don't want the final answer. I want you to tell me how you get to the final answer. Where do you start from, not where you end?
That's going to be the acceleration of the center of mass plus the angular acceleration across RQ minus R bar. So acceleration of center of mass, it's measured in G, plus the angular acceleration from this to ground, cross RQ minus R bar.
Okay.
Plus the angular velocity from this to ground plus the angular velocity from this to ground plus RQ minus R bar.
All right. Very few things to remember. Again, I don't mean memorizing them. I mean knowing that they exist and you can use them. Now, these, let's see. These I had it before. And you guys need to tell me again because I don't have it. Acceleration of center of mass was probably, since the velocity was r theta dot ex, that was r theta double dot ex. Correct? All right. Angular velocity of the disk with respect to the ground. I'm sorry, not angular velocity. Angular acceleration, alpha. What do you want me to write there? Theta double dot big EZ cross with, what is this vector again? For the fourth millionth time, REY. And this is theta dot EZ crossed with theta dot EZ, which is crossed with REY. Right? And that gives me r theta double dot big Ex EZ crossed with y minus Ex. Ex, okay? I don't want to skip any steps here. Really don't. Ex is z crossed with y is another minus Ex. Okay? I'm gonna start going down here. I can't write in that weird position. Okay. I hope that's a plus. I thought that was a plus, right? So this goes away. Okay. Don't need to rewrite all that. What am I left with? EZ crossed with EX, which is an EY with a minus R theta dot squared. What did I say? EY. That's all I have. Acceleration of the point Q. Now let's go back to basics here. Remember, this is rolling. This is not a hinge. The kinematic condition for rolling tells me that these 2 points, the one on the disk and the one on the ground, two rigid bodies, they're touching each other on a point. They happen to share the same velocity. It doesn't matter from which reference frame I look at them. Velocity only. It means that this thing at the next instant in time has gone down the incline. It's not hinged here. It will go down. So this point Q has moved somewhere else and is not touching anymore. It will be another new point Q that is touching. So it has zero velocity because that's how we define rolling. It cannot have zero acceleration because if it does, that's hinged. It's not going anywhere. And that is not what is happening here. And the fact that the acceleration, if you look at that, it's pointing opposite to EY. So this acceleration of point Q, this would be your vector acceleration of point Q as part of the disk with respect to the ground, is pointing to the center of the disk, right? That means this point Q on the disk has zero velocity, but there's going to be a delta velocity in that direction. And in fact, it's going to lift up from the ground. If you think about this, next it's going to go away from the ground. It's not going to touch the ground forever. So that makes sense. Okay, that's rolling. It's not zero. It cannot be zero. If you get a zero, there's something wrong. Okay, so let me just copy it here.
Since the acceleration Q is in direction of the center, shouldn't that always be the small EY?
No. Because
Well, I've used the old vectors expressed in the coordinate.
I'm saying if it's moving, the disk is moving, a point is placed on the disk, its acceleration will be towards the center. So in that sense, when we have a reference frame in that direction, so this EY can
No. Reference frame, coordinate systems are two different things. So are we talking about coordinate systems? I've expressed everything in the ground fixed coordinate system. Agree?
Yeah.
Okay. So if I use that coordinate system, the acceleration of the point of contact, Q, as part of the disk will always be pointing normal to, it doesn't matter where this disk is going to always be pointing normal to the ground. Doesn't matter what you do.
Is that is that the case when we take it in the disk reference, disk coordinate system?
Yeah, you will
Acceleration will always be towards the center.
It will always be towards that point. Yeah, it's a vector. A vector is a vector. It doesn't matter which coordinate system you use. The coordinate system is just a way for me to implement and write it in a way that I can understand it. But that arrow is always pointing that way.
So we still get r squared theta with it.
You will get the same magnitude. This is the magnitude of your vector, and then instead of big y, you will have projection in this small ex, small ey. Yeah, you can do it. You will have sines and cosines of theta, but yeah. So this is what I have. Okay. Well, now I can do it. I can apply the second law of Euler with respect to another point. Because, and I hope I didn't make any mistakes, because it will be fun to get a different result now. If I stick all the pieces in there, last equation, I have 3 over 2 mr squared theta double dot big Ez is equal to mq mg r sine of beta big Ez, and then I probably have to do something there. I have a minus r ey. We said that r bar minus rq is r ey, right? Which is crossing the mass times this vector here. Remember, this is the mass of the entire disk, right? Oh, cool. What happens here?
Second part goes to 0.
Yeah, just a few times in your life you get things that just cancel each other. That's nice. So it happens that you basically could have written the second law of Euler almost like as if it was with respect to center of mass or body or inertially fixed point, because the additional term goes to 0. And so this is my equation of motion, which I can clean up a little bit, divide by r, divide by the mass. So I'll take away 1r, take away the mass. I just want to make it look like that. And it's theta double dot minus 2 over 3. It looks exactly like that. G over r sine of beta, and that's it. Well, equals 0. Right? I can do this because these are the same direction. Easy, easy. So I do get the same equation. If that wasn't the case, that would have meant that I had some errors somewhere, of course. So just picking a point that may be a little more friendly avoided me having to go through balancing forces and doing F equal ma. I didn't even care about the first law of Newton of Euler for rigid bodies, because I picked a point that in this case happens to eliminate all moments of forces that I don't know.
So we always put a point where only one force remains.
You can do whatever you want. I'm not going to tell you what you have to do.
In that case, we won't need first law of Euler. If we
In this case, yeah, right. If there is a point in your problem, that's the question. If there is a point where the unknown forces, if you pick that point, happen to give you 0 moment, it's probably a good idea to pick that point.
So we follow the pattern that only one force remains, the moment of only one force in the
Well, I cannot say there is only one force. I can give you a problem with 20 forces that you do know, and you still have to compute the moments of all those. But the unknown ones are usually reactions, contact forces you don't know, reactions, static friction. Those are the main ones that you usually don't know. If someone asks you to solve for them, then you have to solve for them. But if someone asks you the equations of motion, you don't really want to have unknowns in those equations, right? So this is a simple 2D problem. So in this case, yes, but if for some reason this rigid body was touching another rigid body here, then you may not have just a single point that eliminates all unknown forces. Of course, problems can be complicated up to a certain point when you solve them by hands. Otherwise, you will go crazy. So is it clear how we did it with respect to another point? Let's do it with respect to yet another point, just for fun. Just to show, because so far I've picked points that are fixed to the body, right? Center of mass, and another point which happens to be the point of contact, but it's fixed with respect to the body. So we discussed last time that picking just a point fixed to the inertial reference frame is probably not a good idea, right? Because I don't see any point fixed to G that is going to allow me to eliminate those forces in Q. There isn't. And so I think I briefly mentioned last time, why don't we pick this point that doesn't belong to any of the rigid bodies, but it's moving just under the center of mass, and it's representing the contact at every time, right? Again, imagine that this disk is leaving a trace with ink or something, and it's describing this line here as you go down. So now it's point Q. Let us pick point Q, which I don't even know how to call it at this point. It doesn't belong to the ground. It doesn't belong to the disk. What do you want to call that point? Right under C at all times. Does it make sense? Do you see what I mean here? It's just that point. Why? Because with respect to that point, I do still have 0 moments. This is the thing about rolling that it really drives people crazy, because you can think about 3 different points at that location. Again, the point that belongs to one body, the other point that belongs to the other body, and then this point that belongs to no one, which is describing the trajectory of contact. But again, it's not a point on any of the bodies. So you can think about those. So basically, my MQ is going to be the same, but there's other things that are not the same. So MQ was whatever I found before. Can you give it to me again? I'm sorry, I erased it. I think it was some MGR. Is it?
Yeah.
Wow, that was good luck. Okay. So now I'll do the same, go through the same drill, and again, we do it in a planar problem. You're going to do it. It doesn't matter how complicated it is. You have computed this once and for all, and then you can play with all the points you want. Now I'm just changing the point Q. It has the same name, but has different properties. Right? So let's start all over again. I need to compute this HQ with respect to a point that seems to be the same, but it's not doing the same thing in space. Because what is different now? Okay, m r squared over 2 theta dot, little z or big Z, same thing. And I've just recopied h bar in G, plus rq minus r bar. We said that that's, what is that? That's rey. It's minus rey, right? Is it?
No.
It's rey. Sorry, ey is down. Okay, now this is crossed with m something. And v bar G was r theta dot ex, if I'm not mistaken. Now this is not 0 anymore. This is just a generic point. What is the velocity of Q now? The same as the velocity of the center of mass. Right? So I should probably remove this D from here. It's not part of the disk anymore. Does that make sense? Oh. Okay. So this goes to 0. Nice. Okay. So of course, if that's my new HQ, which is different from the one I had before, and of course there is a 3 that is missing, right? I think we had a 3 over 2 mr squared theta dot something. So in order to get the final answer, given that HQ is different, MQ is the same, this piece down here will have to give me something different. Otherwise, I'm in big trouble if it doesn't. So the acceleration of Q is different. right? That's the only thing that is different, that can be different. Acceleration of q now is what? Before we had this vector, remember, pointing to the center? Because that was the point q belonging to the disk that is not going to touch at the next instant in time, so we better go away from that position. So it was this something ey minus ey. Now, this is not the same point. They appear to be in the same location, but they're doing different things. So it's like we're sitting on the same chair, but you're going that way, I'm going that way, right? So these guys are doing different things. One point q is going up, and this point q keeps going down the incline. So what is its acceleration? It's a bar, right? It's right below c. That is doing exactly the same thing that c is doing. They're moving together. So that would be r, what is it, theta double dot ex? Is that what we have? OK. So let's put all together, and then hopefully this will work. So if I do the left-hand side, that means the derivative of this here, m r squared over 2 theta double dot, I'm taking its derivative, is z. And I can do this again because the big E's are fixed to the ground, because that's the derivative rate of change with respect to the ground. It's equal to this moment plus minus, what is that? Cross with this term here. OK, good. It doesn't go to 0. Otherwise, I would have started to be a little concerned here. It cannot go to 0. That's the term that needs to make the difference to get the same equation, right? OK. Well, that's that. So what is this going to give me? This is ey cross with the x. It's a minus ez. There is a minus plus. There is another minus minus. So this is going to be minus r mass r squared theta double dot ex. I'm sorry, ez. Yeah. And then here I have mgr sine of beta ez. And here I have the derivative of the angular momentum. It looks like it's the same. If I bring that on this side, I get 3 over 2, right? It better be the same. It's the same motion I'm looking at. So simplify what you need to simplify, you get the same result. Questions? Issues? Concerns? So this was nothing special. This was really a basic, simple, non-realistic problem, just to show what you do. You have F equal ma if you need to, and then you have the second Euler's law, which is this down here. That's the only one. If you really want to memorize anything, just memorize this. The steps are compute h bar, because you have the tables that tell you the moments of inertia. Compute h bar first. Compute the acceleration of the center of mass first. That's your kinematics. And then decide wisely, if possible, which point you want to use. If you're not wise enough, that means you have to use both equations at the same time, which is not the end of the world, but it may be for complicated problems. So I really don't want to do anything else today, because the next time we're going to do a fun problem that you can start thinking about, which is the tabletop, the top. Not tabletop, the top. Now my drawing is terrible, so next time I'll project an image which is already made. Bless you. But you know, this is, I don't know if you ever played with these things as a child. Maybe you still do. I don't know. This would be I have to. I have no choice. Not because I'm teaching this class. It's personal stuff. So, and we'll have to pick some axes here. So the next time we'll focus on this. I invite you to start thinking about it. I think that's what I picked. EY, EZ. So this coordinate system here, this is point O, is fixed to an inertial reference frame. So EX, EY, EZ, EZ is pointing down, is fixed to an inertial reference frame. And this is the top, of course, that it's can spin, and we want to find the differential equation of motion of this. This is a full 3D problem now. There is one point. This point remains fixed, so you can definitely look at, in principle, only the second law of Euler, d dt in an inertial reference frame of h o n is equal to mo. So there will be, of course, a center of mass here somewhere. The tops are usually symmetric bodies. So if I cut through this symmetry axis, say that I see a circle, circular section, doesn't matter. Well, it does matter actually for the way I will do it. So, well, if you want to do this problem, the steps that we're going to see, but it's good to know the steps before you implement. There is gravity, of course, here. Otherwise, it's not fun at all. So mg is acting definitely here. I'm just going to, have a conversation about this. I'm not going to solve it today. But, you have a couple of days. You may want to look into it. So I have that force there. There is some reaction here that acts on the top at a point O, which is fixed. And so what are the things you need to do? Well, we will have to compute h bar in n, which is going to be your inertia tensor of the body, let's call it r, times omega r n. So we're going to start from this. We don't even attack the acceleration of center of mass because we'll see this is sufficient. Now what you need to understand is that this is kinematics. When you're writing h bar, except the fact that there is mass properties in this tensor here, you're doing kinematics. You have to find omega. So what you're doing, every time you write this, you are parameterizing the h bar as a function of whatever variables that you picked for as coordinates for your motion. So in this case, I think what I'll do is a 3-2-1 Euler sequence of Euler angles. And so basically, you will have to write the full expression for omega for a 3D case with 3 Euler angles. Figure out what this is, inertia tensor, find h bar, and then we'll probably do it with respect to point O. Have you ever seen this problem before? Yes.
The rotation is about the imaginary axis, or is the rotation about easy also?
The rotation is about any axis. This thing is free to move and rotate and do whatever it wants. The point, about point O, yeah. So it's a 3D motion. What tops usually you give it a spin here, and then you put them down, and they start doing this kind of weird motion. Point O is usually not constant, but I'll bring you a toy I have which keeps it constant. I have a gyroscope toy. You really can see that motion. You can put this in a small concave surface so that that point doesn't move. And if you're careful enough, it may kind of stay there.
Just out of the context question,
Yeah.
when we actually rotate a top, does the point O always follow the same direction for a value of omega which is constant about that imaginary axis?
No, I never said that omega is constant here. I never said anything. I want to find the differential equations of motion. I don't know if it's constant. It's probably not. What happens when you have a top? You put it down. Assume that the point remains fixed. You're so good, or you have a way to just keep it there, right? The thing will slow down and fall at some point eventually, right? There is friction. And that's what I'm trying to represent here. So again, it will be easier seeing the actual physical system, but if you're able to constrain this point, this object is in general exchanging forces with the table, whatever it is that I'm calling the ground. And so when I said that there is a generic reaction here which is pointing who knows where, I'm just telling you that I'm modeling the interaction between the top and the ground with one reaction which is a generic reaction, right?
But the top will not fall. If we are giving it a momentum at a particular angle,
It will eventually fall. It will eventually fall in real life.
Take the point. Because top starts falling when it starts to wobble.
Yeah, right. But that's the case that I'm addressing here. That's the case that I'm addressing here. I'm not putting it straight up, and even if I put it straight up, it will eventually slow down and fall.
No, even if it slows down, it will not fall if we are contacting the point, because before that, it was rotating at a particular angle momentum and it slows down, it lost energy, but it was at that point. It slows down in that motion only to stay at a particular point of it.
So you're saying if you put this up like this, right?
And rotate it.
Yeah, ideally it will only slow down, but nothing is perfect. So ideally it will slow down and stay there like this. Yeah. Yes, yeah. And that's what you will get from equations, but nothing is perfectly symmetrical, so it will eventually fall. And so what I'm trying to represent is a general motion where I spin it, I put it down at a generic angle, this thing starts moving, and it starts moving because there is the force of gravity, which is going to contribute to the moment with respect to, for example, this point. This doesn't, but the force of gravity is causing the top to do that wobbling motion that you mentioned. Yeah, we'll see it. I'll bring a physical system actually, and we'll model it like this. We'll simplify things like this. And even if they're simplified, you'll see it will get a little complicated because you're doing 3D rotation now. And this is only a rotation. There's no translation. I'm assuming there is no translation because I'm saying that this point remains fixed. Well, it looks like I'm going to let you go before the time, unless you guys have any questions at this point. Are you starting to solve problems from chapter 5?
After the exam on Wednesday.
Okay. You all have the same exam?
A lot of people here.
Okay. Again, don't wait, because if you wait, what you have captured in your mind from the first part of the class, which is extremely important for this part, again, unfortunately, you cannot just throw it away. It will kind of start vanishing and you will struggle double because you have to go back and refresh that stuff, which at this point should be easy, quick. Maybe you don't remember these formulas. I check them. I mean, sometimes I have minuses instead of pluses. I check them all the time. But you need to know that they exist. You need to be able to go to them right away. Okay, I'm done for today if you don't have any questions.